And what we found is that this cometary nucleus doesn't look at all like what we thought a comet would be. Not only are there no two identical planets in the solar system, but there are no two identical systems either. Everything you do, what you eat, consume, vote for, and more. Impacts on the biosphere affect you. When we say man makes history, that's what it means. There is no plan B for mankind on Earth.
Hello everyone, welcome to this new show. Today we're going to talk about exoplanets. We'll also talk about the origin of Earth and answer a question that many people ask themselves. Is there life elsewhere or not? To answer our questions, Jean-Pierre Bibring is today's guest.
Hello, thank you very much for inviting me to talk shop, as they say.
Thank you very much. So, for those who don't know you, could you briefly summarize your profession, what you have actually done, the main projects you have worked on?
First, I'm entirely a product of the university system, having completed my studies there. I climbed the ranks in teaching because I wanted to do both teaching and research. It was at Orsay, it's still at Orsay, which is now called Paris-Saclay University, but it was one of the universities in Paris. And I studied physics first, nuclear physics. And when I had to actually choose a direction, it was the time when the first lunar samples were arriving. It was during the American Apollo missions and the Soviet lunar missions. Et donc, I realized that what I had learned in physics allowed me to get into what was becoming more and more exciting, which was analyzing extraterrestrial samples that had been collected either by men during Apollo or in a completely automated way by the Soviets. And I started working on those things. And gradually, I got more and more involved in what we call space astrophysics, which consists of making instruments that fly in space to observe either deep space or our own solar system. And I focused more on the space exploration of the solar system, which is something that started in the 1960s, so it already existed when I began. But we gradually developed the means to go and observe, one after the other, the planets of the solar system and other objects, small bodies, comets, and asteroids. So I got into that field, and we even created a laboratory in Orsay called the Institute of Space Astrophysics, where I'm still based. And we participated. I was involved in the exploration of the solar system in almost all the major adventures of those decades. We have things that have flown and are still flying around Mars. We've done quite a few missions like that. And what I really liked about it was that the more we discovered things, because these are real discoveries, the more our understanding of what Earth is has evolved. And today, we've reached a vision of what Earth is in terms of its formation, its evolution, and its properties. Completely different from the one we had, and the one I had when I started this profession.
All right, so you mentioned missions for observation. When we talk about observation, are we just talking about telescopes flying over, or are we also talking about probes that land?
Both. That is to say, space exploration, which is about trying to access the properties of what we can observe, does this in different ways. We can either fly by something very quickly, which is what we call flybys. We can stay in orbit around these objects, but at a certain distance. We are in orbit a few hundred kilometers from the object. From a distance, we will probe properties across the whole surface, not just the atmosphere, if there is one, or even the subsurface. And then there are cases where we can actually land on it, and at that point analyze a certain number of properties locally. And in fact, what's really effective is when we can combine all of that. If you only do remote observation, you don't necessarily have the precision you can get when you land. When you land, you have precision. You can actually go down to the microscopic scale. Each grain, we can analyze it, but that's local. And then, of course, we need to know how we can extrapolate what we see there to the whole planet. And so now, for quite a few objects, the Moon, of course, but also Mars and other objects, we actually have the ability to combine the global view and the local view. And that's what allowed us to understand the formation and evolution of these objects. Mars is emblematic, of course, because there have been so many missions to Mars. And we have both a global view of what Mars is throughout its history, and we've been able to show that there were different eras in the evolution of Mars, that there were times when Mars had liquid water on its surface. Very likely, and that all of this has disappeared. Can we explain why? And now we can try to land in sites that have preserved the memory of those ancient times, when Mars had water on its surface, for example, and find out if there was a chemical evolution similar to what, on Earth, gave rise to what we call life.
All right, so among all the missions you've worked on, there's one I find particularly remarkable, which involved landing on a comet. Could you talk a little more about it? Did you work on it?
Yes, of course, if you want. As soon as we had the means to look at other objects, as I said, we started with the planets. And very early on, the question soon arose of also trying to reach smaller objects, which can tell us very different things about the formation processes. And here we're essentially talking about cometary objects. And so the idea of going to rendezvous with a comet was born very early on, actually, in the 70s and 80s. And the first mission that took place was a flyby mission of Halley's Comet. You know that Halley's Comet orbits every 76 years, and it was coming back in 1986, very close to Earth. And so there were several observation missions, and it turns out that was my first mission. In fact, I was able to take part in those flyby missions, and they were truly extraordinary missions. In a way, because the relative speed was so high, 70 kilometers, between the moment you're in front and the moment you're behind, it's 2 minutes, which means you have 2 minutes to take all the measurements. Well, so you can imagine a little bit what that means. It's very exciting, but actually very complicated and very demanding. It can be very frustrating. And we did that. I took part in the missions with the Soviets because there were 4 probes, 5 probes that were used, 2 Japanese probes that mainly observed the plasma tail, and there were 2 Soviet probes that had. The goal is to pass within a few thousand kilometers, which is quite close. But to increase the observation time, there was even a platform that was constantly pointing during the 2 minutes, and there were 2 of them. The Soviets always sent 2 probes for the same goal. And so we had an instrument on board made in France behind the 800, which was there for the first time, to actually characterize the nucleus of the comet, because we were entering the coma into this atmosphere. And thanks to that mission, the European Space Agency's probe Giotto was able to go straight ahead because we gave it enough information to know exactly where to go. It didn't have any way to aim, but it got as close as possible to try to find out what it was. And so all of that gave us a huge amount of information. It was a real upheaval, in fact, regarding our understanding of what the nucleus of a comet is. We had no idea what a comet actually was. We know that when the comet passes near the sun, it develops this coma. That's what we call a comet, this atmosphere and these big tails, because there's ice that essentially sublimates and that produces the gas we see behind it. But we didn't know much more. And then suddenly we discovered a number of things, including the fact that there's some very interesting organic material, but we hadn't expected that before, so we didn't have the right instruments. And besides, in 2 minutes, it's complicated to analyze this material. And that's where, in fact, in Europe, we were supposed to do it with the Americans who left the project. A mission was born to encounter a comet nucleus and even drop something onto it. So we came up with this idea in the 1980s, and that's how, after a lot of setbacks, actually, the Rosetta mission was born on a purely European basis. Initially, we even wanted to land on it, take a bit of the comet's nucleus and bring it back to Earth to carry out a comet sample return mission, which has never happened since, by the way. But since we were doing it with the Americans, who left the project without even telling us, to be honest, we decided that if we couldn't bring the samples back, we would bring the laboratory there. And that's how this very interesting combination of Rosetta and Philae was born. So Philae is a module whose goal was to go to the comet attached to the main module called Rosetta, and then when we weren't too far, to be released to land on it. And it happened. After quite a few setbacks as well, the launch took place in 2004, and it was in 2014, after 10 years of cruising, that we were able to land in December 2014, November 2014, on this nucleus. So I was quite involved in it since I was the scientific co-lead of this descent module. There were 2 leads, a German and myself, because it was actually a very international adventure, very cooperative, and France, Germany, and also the Italians, by the way, were very involved in this project. And so it's the first time that, but you see, these are technologies from the 1980s that we put in place. And we landed 30 years later, considering the time it takes to design, to develop, to get there, and so on. And so it's a success that I find quite extraordinary in a way, because back in the 1980s, when we knew nothing about a comet's nucleus, we didn't know if we would sink in, if we would slip, if we would bounce. We had no idea what it was at all. We had to design a system that could adapt to whatever we would find there. In the end, it mostly worked well. Some things didn't work out, but others did, especially regarding energy. We finally landed, though it bounced, if you recall, It was an extraordinary adventure since we hadn't planned for that material. We feared sinking, which would have ended things and cut off communication. And actually the opposite happened. We bounced, but we bounced with such speed that we bounced several times and then finally settled down. We ended up in an alcove that had never seen sunlight, and we were able to start analyzing that material. And then there were discoveries. Maybe we should have talked more about them, because the fact that we actually got there was so spectacular that people didn't really ask afterwards. So what did you find? And what we found is that this cometary nucleus is nothing like what we thought a comet would be. There's very little water, for example, even though we thought water was the main component of a comet, that it was that famous dirty water that had been identified. Of course, there is a little bit of water, and that's what gives rise to the coma and the tails again. But most of the material is organic matter. It's matter made of carbon, macromolecules, even organic grains several millimeters in size, which we've shown in our images. I believe that in this book I must, and I hope I do, give some images of what this comet nucleus looks like. This material, regardless of its orientation, that's Philae's foot, this material is very, very dark. By the way, to make an image like this, you have to stretch the channels because it's so black, it's blacker than coal. It's really organic matter. And that's when we realized that this material, which we couldn't fully analyze, by the way, and that's why currently, with other missions, we're trying to analyze this material, especially by bringing back samples of this type of material. We did it with the Japanese, among others. Maybe I'll discuss it later. We realized that indeed this material must have been essential in guiding the evolution of carbon chemistry once some of these grains entered Earth's primordial oceans, because some properties of these grains, which are not at all generic properties that are found everywhere in the universe, which also result from the evolution of these objects, even before they could enter the inner solar system and before reaching Earth in particular, which have properties that could actually shape the chain of chemical reactions that lead to what we call life on Earth. And so it was quite a major revolution in our very understanding of what evolution is in general, and especially the evolution from chemistry to life on Earth. A large part of what many people are doing now, and I myself am still involved in it, is to analyze this material as thoroughly as possible. We have ways to access some of these molecular chains, and maybe I'll tell you about one or two of them, because we find some pretty funny, let's say, interesting things. But now we're working on it, and that's actually one of the things we're doing with the Japanese. On an upcoming mission, which will actually involve going to a cometary nucleus, taking that material and bringing it back to Earth, to take advantage of all the technologies we have on Earth, to really go in depth into what was probably at the heart of the evolution toward life.
So what are the special properties of the materials we found in these comets?
Again, when we say there are organic grains, it means that, carbon is an element. We know well what carbon is. Electronically, it's an element that easily bonds with others, with hydrogen, oxygen, nitrogen, and so on. So what we call organic chemistry is all the chemistry that's based on the ability of carbon, generally in space, but also on Earth, to react and form macromolecules that can polymerize, like polyethylene and things like that, right? All of that is based on carbon chemistry. We know that these grains are essentially made of these kinds of structures, and we discovered through the Rosetta mission a very large number of molecules based on carbon, including amino acids. Glycine was detected, showing a whole chain of reactions like that. But that's the big frustration with this otherwise amazing mission. We still haven't found the properties that seem essential to us. I'll give you an example to show you both the potential of these things and the frustration involved. You may or may not know that in the human body, of course, we have a lot of organic chemistry, including amino acids and proteins, which have very particular properties, one of which is called chirality. We won't spend too much time on this, but chirality refers to molecules that are made with a bunch of the groups that attach to them, and they can be on one side or the other of the molecule, essentially. They can have different shapes, just like your two hands. They both have 5 fingers, but you can see they're not superimposable. They're only superimposable in a mirror image, and that's what we call chirality. Well, it turns out that in the human body, Certain molecules, especially amino acids, all have this same property. They rotate light, as we say, in one direction and not the other. They have specific properties. It's as if there are only left hands. There are no right hands from the point of view of amino acids. Sugars are the opposite. They are all right-handed and not left-handed. Well, when you do a chemical reaction and make these things, you produce just as much of one as of the other. In principle, you create racemic mixtures with equal amounts of each component. Living organisms have managed, you could say, this feat of eliminating, for amino acids, all the right-handed ones, keeping only the left-handed ones. And for sugars, all the left-handed ones are eliminated, keeping only the right-handed ones. Where does that originate? What is the initial property that led to this specificity in Earth's organic chemistry, so that in what entered living organisms, a selection took place, probably very early in the system? Well, we think that part of this is due to chiral excesses that were already present in the grains that arrived on Earth. And with Philae, we had the means to analyze these excesses. And for essentially energy-related reasons, linked to the fact that we ended up in an alcove where there was no sunlight, we couldn't recharge our batteries. And so we worked for 60 hours, which was already very good. Our first experiment, if we had recharged our batteries, would have been to measure these chiral excesses, to find out, as we thought and as we still think, that it was probably properties of the disk that gave rise to the solar system, properties that certain radiation from the young sun could have altered in those grains. It's these excesses that later on ended up in the primordial Earth's oceans. Given the composition, it's not just the water, but the ingredients that were in those oceans that could have favored a chain of evolution which selected one form over another. And that's what led, among other things, to the understanding that all of chemical evolution happens like this, with ingredients that sometimes are far from the dominant ones. Just a tiny bit is enough. It can be a minor or trace element, but it will have an essential effect on evolution afterwards. So that's how the Rosetta and Philae missions set in motion. A lot of things are happening today in the way we rethink evolution in a broad sense, and especially the evolution of carbon chemistry towards life.
So that brings up another question for me. This comet, does it belong to our solar system or does it come from somewhere else? No.
No, there can be objects that come from another system. No, most of what is in the solar system today formed very early in the system from the material that was in that disk, with very little material coming from elsewhere. Then the whole evolution of this disk, and especially all the collisions that could have happened, the accretion from small grains to form large objects, all of that is something that happened 4.7, 4.8 billion years ago around the sun. Most of the mass went to the center to form the sun, but everything else gave rise to the millions. The billions of objects that populate the solar system, the planets, of course, the 8 planets, but also all the other small objects that have accreted. Some of them disappeared due to collisions or even left the solar system, but today's comets are the remnants of what formed very early in the evolution of the solar system.
So if these are the remnants of what formed quite early, does that allow us to get additional information about the formation of the solar system in its very beginnings?
Of course. The fact that there are 4 inner planets, so Mercury, Venus, Earth, and Mars, instead of just 1 or 10 or 1,000, that's important information about all the dynamics that could have happened, gravitational instabilities, planetary migrations. These are words that may not have yet sunk into everyone's consciousness. But, we've always stuck with this idea, for example, that everything is very static, that there's no evolution at the center, the same dynamics of things. Of course, we realize that it's actually the opposite. There's a dynamic evolution that's absolutely essential. And, for example, we think that all planetary movements are regulated, as they say, like clockwork. That is, the Earth always rotates in the same way, that it has always rotated like this, that it spins on its axis in 24 hours around an axis, supposedly at 23 degrees, which isn't accurate, etc. No, in fact, the more we learn, the more we realize that all of this results from a whole set of dynamic evolutionary effects that have taken place very early in the system, and which have lasted but continue to evolve. And it's this evolution that's very interesting. And so this initial dynamical phase in particular caused a lot of collisions. And when you have 2 objects that meet, depending on the speed, if it's at low speed, there will be accretion. They will grow. And that's how the Earth grew, like all the planets. If the impact is stronger, on the contrary, it creates dust again and it can disappear. So this movement is very important, and that's what we're studying right now. Both through observation and modeling, there are now modeling techniques and people doing extraordinary physics grounded in mathematics to set up, to simulate everything that could have led at some point to a system like ours, with 4 inner planets and 4 giant planets. Whereas now, and this is one of the great discoveries with exoplanets, we now know that most of the stars you see at night are surrounded by planets. But there aren't 2 alike, meaning not only are there no 2 identical planets in the solar system, but there are no 2 identical systems. And this idea of extrapolation that we all had, because when we only knew about Earth, we assumed that all other worlds were the same, so we extrapolated. And that's why there was the famous plurality of worlds. And many people since antiquity have suggested that the same thing exists everywhere. Now that we've explored the solar system, we're starting to understand that no 2 are alike, and more importantly, we're beginning to understand why. What made Earth become Earth, Mars become Mars, and so on. And now what? Thanks to the discoveries of exoplanets, after the major discovery by Michel Mayor and Didier Queloz in 1995, we've realized that indeed there are exoplanets absolutely everywhere. But at the same time, and maybe this is the most important part of their discovery, which I find extraordinary, is that there aren't 2 that are the same. That is, the solar system is absolutely unique as it is. What makes all the systems different? It's exactly what we call a system. The arrangement of matter in the form of planets or small bodies results from phenomena that are present everywhere as phenomena, but which take on particular forms at any given moment. And because in space, it's these forms that will ultimately determine the final structure, which isn't really final but current, and which keeps evolving. Well, that's what creates the diversity we see. So now we understand that diversity is the new paradigm. Instead of being able to extrapolate what we see to say that there is a plurality of worlds, that it's the same everywhere, we actually realize, on the contrary, that the processes are the same. It's always collisions, gravitational interactions, whatever you want, but the form it takes is completely contingent, meaning it depends on the context. You add just a little bit more of this or that, you change a tiny parameter, and suddenly you get a different evolutionary path. And what I find extraordinary now is the famous chance and necessity. We're starting to weigh the respective role of determinism. Physical laws, a physical law is deterministic, but it depends on the initial conditions. The initial conditions are never the same from one to another. There are always minor differences. If someone takes 10 penalty shots, they can't repeat the same one because the grass or their finger position changes each time. We'll do something that the famous idea of chaos, at some point it's going to diverge. If you serve 10 times in a row in tennis, they'll all be different because just a tiny little thing is enough for the trajectory to be different, regardless of the draft simply, and the draft as well, by the way. So as soon as we start to show that, superimposed on the determinism of the laws of physics, there are events that are unpredictable in themselves. That's what we call chance. Each one is determined by physical laws. When 2 objects collide, like when Earth collided with a large object called Theia, very early in its history, just a few tens of millions of years after it was formed, the trajectory of the Earth, the trajectory of Theia, they are determined by the laws of gravity, but you have no way of knowing that they are not correlated. The fact that when Theia arrives, the Earth is in one place rather than another in this orientation, rather than that, it will give you a particular orientation. From the impact, a different point of collision, you change just a tiny detail, and suddenly the result will be completely different. And the evolution of the Earth will be incredibly dependent on that impact, for example, which gave birth to the Moon, but there are plenty of other impacts. A large part, the plate tectonics we have today, the fact that there is water on the surface, all of that is directly linked to certain properties of the impact that the Earth had with that object. And if there had been another kind of impact, well, not another kind, but an impact with different parameters, a different mass, a different composition, a different angle, a different impact speed, we wouldn't be here to talk about it.
It's true that it's counterintuitive, because from the outside, you might think that all the planets in the solar system were made from the same materials. And each planet is different. Even if you look at just one planet, its moons still look completely different from one another.
That's what's extraordinary. You know, for example, the JWST telescope is currently taking absolutely incredible deep field images. You have to be careful with the beauty of the images, because what do the images actually tell you? All the dots you see when you look at the deep field, those are galaxies. You might want to say it's the same everywhere. Our galaxy isn't unique. The proof is that there are as many of them as you like. We can say, in fact, that when we talk about billions of billions, we say it's infinite. No, billions of billions still isn't infinity. Probability-wise, that's not enough for someone just like you to be saying this somewhere else. But still, there are billions of billions. So on a large scale, it feels like it's the same everywhere. And that's a bit like what you're saying. Namely, not only do the structures seem the same, but the ingredients are the same too. And it's true that the atoms we know, hydrogen, carbon, and so on, they exist everywhere, though not always in the same amounts. Stable elements are more consistent, while radioactive ones vary, but the same ingredients are found everywhere. And so, as long as we don't have the ability to look closely, meaning to zoom in on what we see, well, from those images, we can come to the idea that there's an incredible uniformity in the evolution of structures, and that the structures are the same everywhere. And so the plurality of worlds, the fact that what led to the creation of Earth could also happen elsewhere, we assume its existence elsewhere due to the sheer number of cases. That was true. I mean, it was true as long as we didn't have the means to go and explore things, to zoom in precisely on what the solar system is, on what the other systems are, and to understand the reasons for what comes out of this zoom, that is the diversity. The fact that we observe diversity, which we didn't know before we went there. 50 years ago, we didn't know. When people said there was water on Mars, or that there was life on Mars, there was nothing that allowed us to say whether there was or wasn't. And actually, what's surprising is that there was no information that allowed us to say whether there was life elsewhere or not. It wasn't in the realm of science. It wasn't a scientific approach. It was purely dogmatic. Why? Because we wanted to refer to ideas that had been passed down through generations in our societies. With our 2 millennia of monotheism, there was still this idea that there was some act of creation behind it and so on. Now that we can go and see, we realize that the reasons for this diversity reflect it precisely. The role of unpredictable phenomena in evolution, what we call chance events, is major, even if their effects are major, while the factors themselves are not. I mentioned chirality earlier. It's the same as what I said about Thea's impact and planetary migration. You know, why all the systems are different, the planetary systems, stellar systems, exoplanetary systems, let's say. Why are they all different? Because once the disk starts spinning and contains matter, differences arise. Once you accrete an object, it will interact with both other solids and the disk itself. That's why the objects begin migrating, moving and eventually ending up near their star, even though they formed far away. Because for an object to be able to accrete gas, it needs to have a large core. To have a large core, it has to form far away, to have not only mineral grains, but also ices. The farther you are, the colder it gets. If you have a lot of ice, you quickly get a mass such that the gas will be accreted. That's what gave rise to the giant planets Jupiter and Saturn in our solar system. But once you have that, that planet has no reason to stay where it is because it will continue to migrate in the solar system. And you can easily have planets that, through this migration, end up very close to their star. Not too close or it would disappear. There's a very small limit, still well inside Mercury's orbit in our solar system. A limit that means this planet can stay there for billions of years, potentially. And so, when you observe a giant planet with a large mass very close to the star, it doesn't mean it formed there. It means it migrated to that spot, and it will stop when there's nothing left in the disk. Material leaving the disk depends on the protostar's evolution, etc. So when you put all that together, it creates an incredible diversity.
But it's true that I find it's an idea that's hard to get out of my head. The idea that there are lots of worlds that are identical. I came across a magazine the other day that showed a bit of Mars and the different stages of Mars, and it showed the earlier stages of Mars. And actually it was more or less our Earth, but a little bit different, as if in fact all the worlds were identical. It's just that the worlds were at different stages of their evolution, but basically they were just Earths, either future Earths or past Earths, but in any case, Earths.
What can I tell you? Well, what I can say is that I try. I've spent time on it, and it still amounts to a whole book. For historical reasons now, and almost philosophical ones, we have a hard time getting away from the idea that there are Earths everywhere. Because we've spent so many centuries projecting Earth's characteristics onto other worlds we didn't know yet. Now, when we try to understand that evolution is full of different evolutionary paths, different evolutions, we still try to always realign ourselves with that previous idea. We find something, we try to fit it in there. So we might say that the Mars stages are an earlier stage of Earth. We can put it that way, except it's not true. It depends. That's not accurate or the right way to say it. It depends on what we mean by Earth. If Earth is just an object of a certain mass at a certain distance from its star, then there are as many as you want in the universe, of course. And that's why this allowed us to justify extrapolating from other worlds to what Earth is, possibly at a different stage of evolution. It's because we were convinced that what drives evolution is indeed this kind of property, a small number of very significant properties, like dimensions, size, and distance from the star. But we know that's not true, that most of evolution is a bit of that, but a lot of other things as well. And these other things are, for example, the properties of radioactivity inside the Earth. What makes water stable in its liquid state? It's tectonics. What does tectonics depend on? Well, on radioactivity, on the levels of uranium, thorium, and potassium. If you take another object that doesn't have the same levels, well, it won't have the same type of tectonics. But tectonics is also, for example, the fact that some of the water that was present very early in history could not only rise to the surface, but also remain in the upper mantle, and that creates a very particular viscosity. What makes the water rise or not? It's not the distance to the star. That's not it. It's mainly the composition of our atmosphere. For example, on this whole question of habitability, I'll come back later to what you were saying about the stages in relation to Mars, because it's directly connected to this. There is life on Earth, and we try to define that by what we call habitability, because a planet is either habitable or not. And what I'm trying to show is that this concept itself is biased, because we always want to come back to this idea that life is a necessary step in evolution. It's essential that there is no meaning or direction. Habitability, through the idea that on Earth water was essential to evolution, refers back to this idea that for a planet to be habitable, there must be liquid water. There is a lot to say about that. First of all, it's not true that water itself is the source of life. Water was useful in the chemical evolution that led to life on Earth. Understand, it's not just H2O, it's what's in the water that matters. If you have an aquarium with clean, pure water and you put a fish in it, it doesn't live very long. Water itself is not habitable. It's the ingredients, the catalysts, what you add to it, that will encourage certain reactions rather than others. But more importantly, what makes water liquid on the surface of the Earth? Of course, it's partly the distance from the sun. There has to be energy coming from the sun. But if we currently look for the possibility of stability around Saturn, as was the case with Titan, for example, we can see that there is 100 times less energy reaching Saturn. What determines the temperature at the surface of the Earth that allows water to be stable in its liquid state? It's not the major or even minor components of the atmosphere's composition. If our atmosphere only had oxygen, nitrogen, and argon, which make up 99.9% of the atmosphere, we wouldn't be here to talk about it. What makes water stable in its liquid state are components that make up less than 0.1% of our atmosphere, including water vapor and carbon dioxide, CO2. But the story of CO2 alone would justify an entire show or a book. Most likely, when Earth was formed, it had a dense atmosphere, like Venus today, with dozens of bars, maybe even hundreds of bars of carbon dioxide. What made the carbon dioxide stay on the surface of Venus? And you know that on Venus, because of that, the greenhouse effect makes it 450 degrees in the shade, and there is no shade, as they say, on Venus. And on Earth, that's not the case. Why is there so little carbon dioxide on Earth? On Earth, there's less than 0.01% of 1 bar of carbon dioxide, even though there may have been hundreds of bars. The carbon dioxide has disappeared from our atmosphere, and in incredible amounts. 99.999% of the carbon dioxide has disappeared. But how did it disappear? It disappeared because water remains stable as a liquid for other reasons. And when you put carbon dioxide in the presence of water, the carbon dioxide dissolves in the water. That's why there's sparkling water. It ionizes. And in the case of Earth, the ions that come from carbon dioxide, that is bicarbonate and carbonate, those pick up a cation, mainly calcium, and it will precipitate in the form of a salt, which we call a carbonate. All the limestone on Earth is our initial carbon dioxide reserve. And it's incredibly efficient. 99.999% of CO2 has become this limestone, to which living beings have contributed as well. It formed the shells of marine species. But a part of that, which settled at the bottom of the oceans or near the bottom, was mainly introduced onto the controlled continental plates. And when the continental plates, through tectonics, sink a little, it dissolves them and re-injects some of the CO2 back into the atmosphere. The amount re-injected is extremely small, as I told you. That was the famous 280 ppm parts per million. So you see that's 0.0002 of 1 bar. So I'm telling you, it's just a few millionths of the original carbon dioxide. If you had a different kind of tectonics, we wouldn't have this concentration. It could be lower or higher. There's very little of it. Well, that tiny amount, along with water vapor, which comes from the evaporation of the oceans, together they increase the temperature by 33 degrees. You see what 33 degrees means for the average temperature, and it would always be 18 degrees. Water wouldn't be liquid, it would be ice, and we wouldn't be here to talk about it either. So you see that to explain why water is stable in its liquid state and plays such an important role, you have to take a lot of things into account. These include the earlier dissolution, tectonics driven by radioactivity, and plate motion caused by the impact. Magma contraction brought some water back to the surface, but about 90% stayed in the mantle, affecting its viscosity. This is why there are 10 plates instead of more. So it's all of these factors that determine whether a planet can or cannot become not just habitable, but suitable for water to remain stable in a lasting way over time. Permanence is also important. What makes Earth's climate stay the same for more than 4 billion years? A large part of the answer, only a large part, is the stabilization of what we call obliquity. The Earth rotates on its axis every 24 hours around an axis tilted relative to the plane of its orbit around the Sun. That axis, which is about 23 degrees, which is of course the latitude of the tropics. Why is it that angle? It's the result of collisions. What makes it stay at this value and not change all the time? It does move like this obliquity. That's what causes what we call the precession of the equinoxes. We don't have time to talk about it here, but it does cause small variations in the climate nonetheless, because the Earth is not on a circle but on an ellipse, which means there are times when we're farther or closer to the Sun. That's what causes the ice ages, particuliers sur des échelles de temps de tens of thousands of years, but it always stays at 23 degrees. So the temperature variations are about 45 degrees at most, which might seem like a lot. Ice ages are no small thing, but it's over long periods, a few thousand years, and the system can more or less adapt. But it stays there. Imagine if, in addition to that movement, there was this movement, and from time to time that axis was pointing toward the Sun. Just imagine what that could be like. And that's the case for all the other planets. Planets have an obliquity that isn't stable. Why? Because, as you know, what stabilizes obliquity was discovered 30 years ago by Jacques Lascar, an astronomer from Paris. It's remarkable. Most likely, it's the existence of the moon that stabilized that angle. But there are moons everywhere, yet this moon has a particular feature. The mass of this moon compared to the mass of the Earth, that's the mass ratio, and it's the highest of any we know. There are moons the same size as our moon, like Jupiter's, but Jupiter isn't affected gravitationally by that. Mars, for example, has 2 moons, Phobos and Deimos, but they're so small that they don't have any effect. Well, Mars's obliquity is constantly changing, and that's one of the reasons why the Martian climate can't stay stable on timescales of millions of years compared to the billions of years of its lifespan. So, when you put all that together, you realize that what drives evolution and what determines habitability involves so many different factors that you can't just assume Earth's evolution is only a function of its distance from its star. And a big part of what people are currently saying about exoplanets, to determine if they're habitable or not, is whether the conditions on their surface allow water to remain stable in a liquid state. But if you only consider distance, that's not enough. Also consider atmospheric composition, as I mentioned, and the stability of these factors over time. So that's a first set, and it's a very small set that shows how evolution will now be enriched by everything that can at some point happen. But it's the same thing in our lives. What explains why you have the job you have today is, of course, where you were born rather than in eastern Bangladesh. That's true. But it's all the encounters you've had, a show you've seen, an incredible teacher, a wonderful program, and so on, which means that at some point your own development wasn't determined by what shaped your DNA. Well, it's the same thing for all of evolution. Darwin's big idea, which most people still don't want to accept, is that from the Big Bang up to us, evolution doesn't follow a straight arrow like that. We're not heading in a specific direction. That was the idea that suggested everything is aiming towards something. And there is still, whether we like it or not, in our societies, it's not the case in Asia, where they have other ideological or philosophical references. It can't help but go from A to B, and in that trajectory, life is one of the stages. And that's why, at a certain point, even though what Darwin showed is that there is never an arrow, evolution doesn't go toward that. The evolution of hominids doesn't go toward man. No one wanted man to exist and for us to be talking today. It's the context that, at a certain point, if there hadn't been the uplift of East Africa, there wouldn't have been, among hominids, the appearance of etc. That's it. That's Darwinism for me. It's about showing that evolution consists of branching at every stage, and that there are a great number of what he called varieties, let's say possibilities, and that the direction will take one path or another depending on the context. The context will indicate which option is more favorable for adaptation. And this notion of adaptation to the context is essential. As the context evolves and it's interactive, a species can change the context, and the context will shape the adaptation of several species, some species more than others, and all of this creates something that we can't foresee or predict. And that's the strength of what we understand today about the evolution of planetary objects. We understand why the Earth became what it is compared to what Mars became. We understand the very principle of the diversity of paths. And in a way, it's like applying Darwinism, not only to living things, but to the stages since the Big Bang. At every moment, there are bifurcations, and we are on one of those trajectories. And the mistake we always make is to think that this trajectory is unique because it was forced by destiny, by fate, by a creator. At every moment, everything needed to go in one direction rather than another is there. And actually, that's the strength of this kind of work in relation to the challenges of this century, which is to say, nothing about evolution is written in advance. Currently, there are challenges on the scale of a century rather than a millennium, particularly with the climate. These challenges are global and need global responses, but our strength is remembering nothing is predetermined. Our direction is uncertain. And everything you do, what you eat, what you consume, how you vote, etc., affects the biosphere.
La biosphère joue sur vous. Et donc, vous le vouliez.
You contribute. When we say man makes history, that's really what it means. And that's the essential point for me. That's what I take away from all this evolution. Regarding the issues, the challenges that lie ahead of us now, especially for young people, of course, it's about believing that enchantment will prevail, because everything you do on an individual level will lead to things that collectively will allow for solutions that are more favorable than others, especially regarding preservation. And above all, in positive interaction with nature, since the idea of extracting ourselves from nature doesn't make sense, even if it's written in Genesis. So we need to be able to. That's why I was amused, if I may say so, to try to work on this question, because it comes from a reflection on everything space exploration has been and is offering us. But there is a concrete result that is coming now in relation to the challenge of this century precisely. What is the point of knowing that we are alone? And so this notion of life, not as a generated process that will take different forms, but as the particular form of the evolution of chemistry, of cosmic carbon, and which took this form. Because it is adapted to the evolution of the Earth, which itself is very unique, I think it is essential. You know, when I wrote this book, one of the questions, actually, there are two main parts in it. There's a part about the paradigm shift regarding this notion of diversity for planets, for exoplanets, all that. Then the second part, which is about saying that among the particular properties of Earth, there's this question of organic chemistry and life. Life being one of the particular properties, just like the tectonics we have, it's a feature very closely linked to the evolution of Earth, to what we call internal movement, tectonics in general. For me, life is the same. When I say there's no life elsewhere, I don't mean there's no organic chemistry elsewhere. Organic chemistry exists everywhere in different forms. Life itself is the particular form. So, of course, once I've said that, it doesn't solve the problem. What do we call life? That's the question. As I mentioned earlier, there are as many Earths as you want. It depends on how you define Earth. If you mean an object of a certain size, you can have as many as you want. But if you want to characterize the Earth by the fact that today we're here to talk about it, with everything that implies in terms of evolution, then you realize that the number of bifurcations is so enormous that you can't find the same thing twice. So it's more than just semantics. It's that now we're able to analyze things so precisely well enough to say that no two are the same. We can evaluate, for example, the probability that there are two strictly identical beings, genetically identical. In fact, the calculation in this case is simple. There are 23 chromosomes. The probability of having two that are the same is 1 in 2 to the power of 23. For a couple, that's 1 in 2 to the power of 46. Each couple has the probability of producing two identical beings. That's 1 in 70 trillion. So there you go. The diversity of the human population is directly related to things like that. So to come back to what I was saying just before about living things as a very particular property, we tried with many biologist friends, I'm not a biologist, to figure out what your definition of life is. What counts as life? You realize that if you put 5 biologists around a table, you'll usually get 6 answers, and why? Because in fact, this notion of living things is an ancestral concept. In ancient times, in ancient Greece, there was a word for living things that's the same as today, Zen. But back then, living things were one of the 2 terms in a binary. There was the living and the non-living. There are living beings, and so on. I can't blame them for seeing a difference between a stone and living things. To them, stones are eternal and unchanging, while living things return each spring. And so there was this binary way of thinking. The ones I blame are the people today who have studied genetics, who have studied biology, who actually understand this, the living and the non-living, force their knowledge into a concept and a binary that no longer has any reason to exist. Because the problem with this binary way of thinking is that if you have a property that unifies living things, you say that living things are characterized by, if you look at all the definitions out there, autocatalysis, self-reproduction, self-something. That already annoys me because what defines living things is that they're not autonomous. It's that living things are constantly taking in either CO2 or ingredients from the outside. If you cut that connection, it's not called life, it's called death. Living things aren't truly autonomous, which is what's interesting. For example, take a tree. If a tree lacks leaves to collect energy or roots to gather nutrients, it wouldn't exist. So the tree itself isn't what's interesting. It's the tree within its ecosystem that you have to compare to something else. And at that point, you realize that the definition of living things becomes more complicated. Especially since defining living things with just this binary means that at some point, this property must spontaneously arise from a world that doesn't have it. You go from non-living to spontaneous generation, which poor Pasteur spent decades fighting against, and he almost completely succeeded. Except that we accept it for Pasteur, but we don't accept it for living things. Yet we still often accept the idea that life arises spontaneously. Creationism, of course, answers the question, but that's not the case. It's unverifiable and not a scientific way to understand the situation. No, so we need to come up with something else to define life. And with all these friends, I tried to find a property that specifically characterizes this particular form of chemistry that is life. And essentially, to put it simply, it's the translation of the code in DNA by RNA, with that code then transformed into function. It's the transformation of this genetic code into functionality, kidneys, eyes, things like that, that will characterize the ability of this particular chemistry that is life. But you ask, what are the molecules that do this? They're proteins, ribosomes, and so on. It's this whole system that will, and you ask, but what is the chain of reactions that will lead to these things? You realize that the chain of reactions leading to these molecules, which have the function of translating genetic code into function, is just as complex as what made Earth become Earth and not Mars or Venus. And so when I say that there is no life elsewhere, It's that the chain of chemical evolution, in the case of Earth, which led to what life is, this chain is so well adapted to this very complicated set of evolutions, most of whose steps we don't even know. We don't know the composition of the primordial oceans. It's this evolution that we're trying to reconstruct now, and that's one of the reasons we're trying to find out what grains fell onto it, to see what would need to be in the water with those grains, and what would need to be added to achieve this result rather than that one. We come to this idea of a gradual adaptation towards something we call life, and finding that elsewhere, even if there are billions and billions, is going to be complicated.
Now, I'm going to say a bad word, but there are a lot of people today who talk about terraforming. I think it's also related to the way we look at Mars and the desire some people have to go to other planets, colonize them, and so on. From our discussion, and that's also the point of your book, it doesn't make sense to talk about terraforming. Because Earth is the result of a history that is unique, that belongs to it alone, and as a result, the life that exists on it is directly connected to this context. So it doesn't make sense to imagine it elsewhere, to try to recreate it somewhere else.
You put it better than I ever could. That's exactly it. If you like, when Elon Musk, to name just one example, suggests that tens of thousands or even more people will go to Mars the day we make Earth uninhabitable, it's an outrageous luxury, first of all. It's astonishing to even dare say that. But in relation to what you're saying, aside from this outrageous luxury, I would say it's a scientific aberration. Man, in his dignity and diversity, is adapted to all this previous history. We might be able to, although I don't think we will, but we could send people to Mars like we sent them to the moon, but they would be in containers filled with Earth's air and eating Earth's food. The idea of recreating on Mars the environment that humans are adapted to, the environment of Earth with everything that means, major and minor species in the atmosphere, in the water, and so on. It doesn't make sense. We're not going to turn Mars into what it took Earth 4.5 billion years under very specific conditions to become. So no, of course, this notion of terraforming comes from a time when we had no idea what evolution really meant. We had no Darwinian understanding of what progressive adaptation to an environment actually is, an environment that itself adapts to evolution, that interacts with it. So this idea is fundamentally wrong. It's no coincidence that this idea was born in the United States. Of course, but right now there's a renewed interest in this kind of thing because it's true that we have a lot of difficulty teaching Darwinism in the United States nowadays. So there you have it. I hope that here this notion of terraforming can be fought, will be fought, and is being fought enough so that we can say, no, there is no plan B for mankind on Earth. What space exploration has shown is that Earth is an incredibly small, confined world with limited resources. We're on it and have to handle it. There's no plan B. And it's once we've understood that, along with the idea that not only are resources limited, but they're also very unequally distributed on Earth. Some places have certain things due to history. What determines why there are mines in one place rather than another? Why are there so many complex and precious metals in South Africa, for example? It turns out that South Africa is a place where there was an early impact. It has a very large impact crater. When you have a crater, why do you have a crater? An object comes in and vaporizes the most volatile material. So it will go into the atmosphere, the oxygen, etc. And the surrounding area becomes enriched in the more refractory, more stable materials, metals. And so you will find a lot of metals that will be locally enriched compared to what was there before, where it was mixed in all that material simply because it remains after everything else disappears. So the history of the Earth is found, among other things, in the unequal distribution of everything. Once we've said that, we have to deal with it. And as I said earlier, because the challenges are global, the responses must be global. We have to transform, and it may seem utopian if I have the time, but I don't think I will. I think it's not utopian to believe in the possibility of changing paradigms. We need to change essential paradigms about how we build our businesses, how we build our societies, how we fight our battles. And of course, I'm thinking of young people who are very mobilized and can be mobilized on these issues. Since the answers have to be global, we obviously think of the climate, but it's also true when it comes to resources. It's true for many challenges, including wars. What does a global response mean? It means that we won't win by force. We're not going to impose ourselves by force. It means ending confrontations and pursuing cooperation. That's something science knows how to do and practices in many fields. CERN exists, and in astronomy, we do it very often. I work just as well with Japanese, Chinese, Americans, and European countries. Why? Because on these topics, even if the way we approach the questions, as I mentioned earlier, even about the afterlife and things like that, is not the same. We accept the idea that we can work together to expand the body of science, that's it. Things that move beyond dogma to be validated by experience and become things we can rely on. So, cooperation must become the way of doing things at every level of human activity. So, of course, it seems obvious when we hear what's happening right now, not only the wars, but also the idea that we have to prepare for wars, increase defense budgets, and so on. Instead of talking about education and food, we end up talking about things that are disconnected from real life. No, I think, yes, we're out of step with part of what is being said in the world. It's not everywhere, it's in our world, the one where we try to maintain privileges gained during the times of slavery and colonialism. So, we need to be able to get out of all that, to accept that there are people who have experienced so many inequalities, not only in the distribution of resources, but also between people. Inequalities created by what history has made with empires in the past. We maintained it by force, but now people reject it, which is good. We need to avoid a major confrontation. And for that, we need to have a practice of cooperation where everyone finds their place. That's why, for example, the idea of retreating inward and doing everything locally, there's some good in that. Eating tomatoes that traveled 10,000 kilometers is tough. But we're not going to recreate the Chinese people's communes where everyone makes their own steel and goods. We need to have a practice of exchange where everyone gets something out of it. There needs to be a real practice of cooperation. This vision of our place in the universe necessarily leads to practices that, in my opinion, are very fruitful and productive in the long run, but in the long run on the scale of a few decades, not on the scale of a few millennia.
So now we're coming to the end of our interview. You brought a book, we've already talked about it quite a bit. To come back to it a little, the book is called Alone in the Universe, There's No Question Mark. For those who watch the interview all the way through, they more or less already know where you're going with this. So here, it goes over the points we mentioned during the conversation and goes a little further, right?
Yes, Alone in the Universe is actually the title that Adele Jacob herself wanted. I kept what's in the subtitle, From the Diversity of Worlds to the Uniqueness of Life. There are two essential parts. The first explains how, from this notion of extrapolating from Earth to the universe with the plurality of worlds, we have now come to the idea that it doesn't make sense, that there aren't two alike, and that we're beginning to understand the reason for this diversity. So first, there's this initial paradigm shift about what evolution is, what evolution depends on, and what the driving forces of this evolution are that lead to the diversity of everything we see. And the other half tries to explore this question, to find out if, among the unique properties of Earth, the different ones that can't be found elsewhere. I also explain why continuing the research is important. I didn't mention it here, but it's essential, especially on Mars, where we have missions that will try to understand in particular how the same ingredients led to this kind of chemistry, so that we can try from there to understand what happened on Earth and how chemistry became life. And the second part is exactly that, a reflection on the question of whether life is not just a particular form of the evolution of organic chemistry adapted to the evolution of the Earth. And that calls into question, among other things, the very concept of life. And that's what amused me and still amuses me. And that's based on that too, not just on theoretical or philosophical research, but on ongoing scientific practice. Space exploration, which we started, among other things, with Philae and Rosetta, which involves trying to really understand what the ingredients were, even on a very minor or secondary scale, which are still present today in bodies that have preserved a record of what happened 4.5 billion years ago. And of course, we think of asteroids and comets. We now have asteroid sample return missions. There are two in particular that I am currently working on. One was carried out by the Japanese and the other by the Americans, and they are currently being analyzed. And we were asked to build an instrument that on site, where the samples are kept, analyzes grain by grain in Japan. This was done mainly from the perspective of carbon chemistry, to try to understand what is special about these grains, which, when injected into the primordial Earth's oceans, may have influenced the direction of evolution toward life. And we found some interesting things. I'll just give you one example. You know that in DNA there are three components. There are sugars, there are phosphates, and there are nitrogenous bases. There's always a problem with phosphates. Where does this phosphate ion come from? Well, we found a very particular mineral formed under very specific conditions in very specific asteroids. So Ryugu is one of them, and Bennu is one of them too. And we've shown that these grains, when placed in water, will release their phosphate, which can then combine with carbon and go on to form molecules like DNA, RNA, ATP, and so on. So there you have it, this idea that in living things, there are elements that are closely tied to the evolution of the Earth. And so life is terrestrial by nature. And if it's terrestrial by nature, then it's also unique. That's the book's second part, about life's uniqueness.
All right. In any case, we'll put the book in the description for anyone who wants to check it out. Thank you, Jean-Pierre Bibring.
Thank you very much. It's wonderful to have the time like this to chat about things that have occupied me for decades. A great pleasure. Thank you so much.